Are we experiencing a touchscreen or display revolution? Since the first capacitive transparent touchscreen was developed as early as 1973, it has been widely developed and stimulated a big change in our daily life. Nowadays, mobile phone, car display, white goods, museums, medical apparatus, and many other applications have been integrating touchscreens and displays into their products. The combination of the screen and electronic technologies are changing the way how humans interact with each other. This display product has been under heavy load from our daily usage, either by the human fingertip touch, zoom, swipe motions, or under stylus stretch or other mechanical stress. Therefore, the surface of the display, as the intermediate, is changing its optical functions including glossiness, reflectiveness, blurriness, and so on. In addition, those damages generated by the human motions are often invisible. Therefore, it causes the loss of several key functions of the surface coatings, for example, anti-scratch coating, anti-fingerprint coating, and anti-fouling coating. If the display has problem, will you return the display? Actually, no. You as a customer will return the product instead. So it becomes very crucial for OEM and its suppliers to perform various testing on the display product. There are currently many existing international standards. However, most of them are classical mechanical tests, and they are not made for human fingertip touch, swipe, zoom simulation. So how does human fingertip interact with display? We first shall understand our human fingers and hands. Human fingers are highly flexible due to the combination of multiple joints and degrees of freedom. They are also viscoelastic, not like metal. The human finger pad has also a very rough skin structure and is not homogeneous. Therefore, the motion pattern of human fingertip is a nonlinear, dynamic one. Secondly, when human hand approaches any surface, it is always with a specific 45-degree angle instead of a 90-degree angle, because human being feels hurt with a 90-degree touch. Additionally, there are also dandruff, fat, or dirt on the fingertip, and we sweat, and sometimes we apply lotion or cream on our hands. In order to have a sensible test result, we should include all those factors of human physiology and the real use scenario, instead of running any test only because it is a standard. Here are the 3 common motions of the human fingertip on the display. Prior to the test, the display sample shall be conditioned for 24 hours under standard atmosphere. The sample shall be cleaned without applying pressure using a standardized microfiber cloth wetted with laboratory rinsing agent. Before any touch zoom swipe test, a homogeneity test with the water contact angle method shall be performed to make sure the display coating is homogeneous. This also helps to define the right testing area on the display samples. 3 parallel lines with 20 drops per line are implemented for the display surface homogeneity test. Display sample shall be mounted in a rigid form and positioned with the help of a transparent cover. With the durability OEM spec as a general guidance, all the test parameters can be set up in a program. For example, the load, the piston choice, liquid supply, airflow function, fabric feed supply, and the cycles. After certain testing cycles, the display sample surface shall be documented and further evaluated with the water contact angle method. A line of 10 drops are applied on the display surface, which covers the abrasion zone. As you know that all kinds of particles, natural and artificial fat, as well as sweat and other contaminants, could easily adhere to the display surface and stay on it. This will not only bring a negative impression on the appearance of the display, but also creates further damage due to its chemical stresses. Human beings then tend to clean and remove such contamination imprints, and therefore by this cleaning procedure, first of all, the so-called easy-to-clean property can be evaluated. Secondly, the cleaning may cause additional abrasion stress on the surface, and this has to be further addressed as well. The fingerprint test includes two major parts: generation of a standard imprint, then the following cleaning. The first step is to transfer a defined amount of contaminant onto a standardized stamp pad. An option of the contaminants is a sebum. The second step is to press the fingerprint piston with a defined load and duration onto the stamp pad covered with the contaminant. By this means, a defined amount of contaminant is transferred from the stamp pad onto the fingerprint piston homogeneously. Finally, the fingerprint piston is then pressed onto the display sample surface with a defined load and time to produce a reproducible imprint. The intensity of the imprint on the display sample shall be designed, documented, and quantified respectively. It is suggested that the display with the imprint shall wait for 24 hours before any cleansing procedure. For evaluating how easily the fingerprint can be removed from the display surface, the display shall be first mounted on any model of Abrex machine. Then, a 20mm test piston covered by the standardized cleaning fabric is used to rub over the middle area of the imprint or fingerprint with a friction pass of 40mm. The cleaning fabric shall be renewed for each rubbing cleaning step. The evaluation of the imprint shall be done for every cleaning step. The evaluation method includes visual inspection or further image processing tool. This test evaluates the resistance of a display surface to scratch damage. For example, stylus scratch test or pencil hardness scratch test. These tests are considered to be most applicable for the determination of display durability from sharp contact tips or accidental gouging during storage. In both tests, control parameters are set at the minimums and then increased until the damage is observed.